What we're going to do today is we will look a little bit more about an absoluteness result for the V alphas. It's an easy exercise. And then we're going to look and see why ZF is not finitely axiomatizable. I mentioned before that ZF, this fact, that though ZF's got countably many axioms, we can't find any finite subset which will do the same job. Nor can I find new axioms to add on to supplement the ones by ZF and hope that finitely many new axioms will also do the job for ZF. So I'm looking at exercise 3.2 to start with, unless you have any questions that you want me to go to straight away. So we're going to need 3.2 in the proof that's to come. So exercise 3.2 here. So as often, we suppose I've got a transitive ZF minus model W. Now we showed a whole lot of things were absolute, things that were simply describable, often with delta zero formulae, would be absolute between such a W and V. And these things I called absolutely definite, or AD for short. So what the exercise is asking is says, show that V alpha in the sense of W is just V alpha intersect W. It's not claiming that V alpha is in W. There's no reason for that to be true, just given these assumptions. But it's saying in ZF minus, I could define the V hierarchy inside this model, and I'd get a whole hierarchy of local V alpha sets. And the exercise is to show that actually what W is picking up by that definition are the true sets that are in V alpha. And there's a hint, and the hint says use the rank function. Right, so that's our function rho. Okay, so this is not, if one uses rho, this is not a long proof. There is more than one way to do this, exercise here. Okay, the hint says, so we use that rho is absolutely definite. So rho is absolute between W and V. If X is in W, then what W thinks is the rank of X is the rank of X. Okay. But now it's kind of one line. V alpha in the sense of W is the collection of things in W which have got rank less than alpha. That's one way to describe V alpha. It's a collection of things of rank less than alpha. But I've just said rho is absolutely definite. So this is the y's that are in W whose rank is less than alpha. But then what is this? This is just things in V alpha here. And this just is V alpha, right? So the job is done, right? Okay, any questions there? You can also prove this without using the rank function, using the result that, we can define V alpha plus 1 as the power set of V alpha and not using the rank function. Okay, let's go down to 311 then. Non-finite axiomatizability of Zf. In fact, we show something slightly stronger than that. We show that actually there is no extension of Zf which is finitely axiomatizable. So let T be any set of axioms expressible in our language. Right? This is our language just with epsilon and equals. And it extends Zf. Meaning essentially that T contains Zf. Let T be a finite subset of T0 be a finite subset of T. Suppose from T0 you could prove every axiom of T. Then the result is that T is inconsistent. So it will be an inconsistent theory. And in particular, if I just have T being Zf itself, it's saying there is no T0 finite contained in Zf from which I can prove all of Zf. Unless, of course, Zf is inconsistent. Right? So that's stated there in the second part. So in particular, if we take T equal to Zf, no finite subset of Zf. So we'll say we'll axiomatize, meaning we'll prove all of the other axioms. Unless Zf is inconsistent. If Zf is inconsistent, then a finite subset of Zf will certainly axiomatize all of Zf, because if Zf is inconsistent, there's a proof in Zf of 0 equals 1 from finitely many axioms of Zf. That can be my finite set T0. So if from T0 I can prove an inconsistency, then of course from T0 I can prove anything. In particular, I can prove all of the other axioms of Zf. So if Zf is inconsistent, there certainly is such a T0. But hopefully it's not inconsistent. Okay. So that's going to be our setup. Okay, let's start on a fresh page. Okay, now I'm just going to pretty much verbatim do what's in the notes. So I won't be writing down anything new, I don't think. Okay, so we suppose that the situation holds that there is a T extending Zf and a finite subset T0 of it, which will axiomatize it all. And then we'll show that T is inconsistent. So I'll say, suppose Zf is contained in T, and T0 is contained in T, T0 finite, and every sigma in T is provable from T0. So I'm going to write that as T0 and use the logical turnstile notation. Right? It's provable in first order logic from T0. Okay. We show then T is inconsistent. Okay, so T on T0, these are formally in the language of sets. And I just write down this instance of the reflection theorem. There are arbitrarily large beta such that the conjunction of the axioms, finitely many axioms in T0, so I've just written them down as one long axiom, one long formula. This holds if and only if it holds in V beta. So this is just by the reflection theorem. Applied to this, and this is the conjunction of the axioms in T0. Okay, so there's nothing new there. Now, T extends Zf. So if I throw in more hypotheses here, I can certainly still prove this. But everything in T I can prove from T0. So actually from T0 I can prove this. So I could replace Zf by T0. So by our assumptions, T0 proves the same thing. Okay, I won't write it out again. But now note, T0 proves this formula. After all, this is just the conjunction of the things in T0. So this is trivial. Right? So from T0, I can prove this here. So that means we must have this holding in V beta. Hence T0 proves for all alpha, there's a beta bigger than alpha. And since it proves this, it proves this. So now we have this statement, which follows from T0. Well, T0 proves everything that Zf proves. So it proves the principle of ordinal induction. So we can look and see what is the least beta 0 in which this formula is true. And there will be such, because in Zf the ordinals are well ordered. So there will be a least beta 0. So by principle of ordinal induction, okay, so provable in the theory T0. T0 is going to prove that there is some such least beta 0, that there'll be beta 0, such that the formula, conjunction there, is true in V beta 0, but in no smaller beta. Pick anything smaller than beta 0, then it's not the case that it holds in V delta. Again, that's just not saying anything more than the collection of ordinals beta for which the conjunction holds in V beta has got a least element. Okay, so we now use the fact, right? We now use the soundness of first order logic. In the form if I got the conjunction of T0 itself proves some phi. And if I know there's a structure in which this holds, then in that same structure phi holds. So here I'm saying if this conjunction holds, then here in some V gamma, then phi will hold in V gamma. Okay? That's because our deduction rules are sound. They preserve truth. They start off from true things and they deliver something that's true. Or they start off with something, if it's true in a structure, the rules say what you can deduce from the hypotheses will be true in the structure. So this is just logic. So what we're going to apply this principle here in quotes by saying, well, from the conjunction of T0, we can prove all the axioms of Zf. So here I could think of this as being an axiom of Zf. From the conjunction of T0, here's an axiom of Zf. Okay, so if the conjunction of T0 holds in this V gamma, this axiom holds in V gamma. And this can be any axiom of Zf whatsoever. Okay, so I apply that idea here. I've got that the conjunction of T0 holds in V beta 0. Right? So I'm taking gamma as beta 0 here. Phi is some axiom of Zf. So I conclude, in the end, every axiom of Zf is true in V beta 0. So from this, we deduce from T0, we can prove every axiom of Zf holds in V beta 0. Okay, any questions so far? Okay, so V beta 0 is a model of Zf. All of our absoluteness results that we've proven so far about absolute definiteness for models of Zf minus, that's going to hold for this V beta 0. It's a transitive model of Zf, which includes Zf minus. So, in particular, appealing to the exercise that we just did. So I'll just make a note, which I've got down there in the course notes. Hence, all our absoluteness results about transitive Zf minus models applies to V beta 0. In particular, exercise 3.1. So from T0, we'll prove, in particular, I pick anything less than beta 0, then V beta, in the sense of V beta 0, is just V beta intersect this W. But of course, this is just a subset of this here. Okay, so T0 proves this elementary fact that V beta 0 is going to be able to prove in its V hierarchy that V beta exists, and the exercise says that's the true V beta. Okay, so the next move then is to say, now I've got that all of the axioms of T0 hold inside this V beta 0, right? Here. So we also have, I see in the notes, I called this star. This is what's called star in the notes, so I could refer back to it. So we also have that T0 proves this bit here. I'm just bringing out this part. It's a little unnecessary for me to keep writing this conjunction sign here. We could just take it as read that this means every axiom that's in here is true in V beta 0. But because it's finite, I can just take the conjunction of these things and just call it one thing. Makes little difference, really. I can't do a conjunction of an infinite set of formulae, right? So for ZF or for T, say, because there's no such thing as an infinitely long formula. I can only do a conjunction if I know the set is finite. So we have that T0 thinks all of these axioms here hold in V beta 0. And moreover, I mean, just to spell it out longhand, as it were, T0 proves there is a beta such that the conjunction of the axioms holds in V beta. Namely, this beta 0, if not others, right? But my point I'm using here in soundness is that here's T0 being true in V beta 0. From T0, I can prove this. So this is true in V beta 0. Hence by soundness again. I have that T0 proves this statement holds in V beta 0. But then what does this mean, right? V beta 0, the following formula is true in V beta 0. It thinks there is a beta in which T0, where the axioms T0 are true in V beta. But this beta has to be less than this one. So then we have T0 proves there is a beta less than beta 0, where the conjunction of T0 holds in V beta. I'm just saying, this is this is going to hold in V beta 0 if and only if it genuinely holds. So this will contradict star. Which said that beta 0 was provably in the theory the least thing in which the axioms of T0 could hold. And here we have supposedly a proof that there's a smaller beta in which it's true. So we've proved a contradiction. So T0 is inconsistent, therefore T is inconsistent. So if a theory is inconsistent, so is any extension of that theory. Now, so is T, which is what we were after. So there's no way we can finitely axiomatize T or in particular ZF. Okay. Are there any questions there? So that's a little section on its own, and it finishes off 3.1. So we'll move on then to 3.2, which is about coding syntax. So it's called formalizing syntax. So, I mean, let's just take pause for a moment to think about what we've been doing, right? We've used our language here to write down a set of axioms for sets, and in which we can express things that we want to about sets. And the claim is we could express all of mathematics using this if we wanted. So axioms, ZFC, about sets or indeed other properties. We talked about inaccessible cardinals, which aren't in ZFC. Or indeed other properties about sets. So we think of V with the ordinals going up the middle. This is the universe of sets, and we have the language which talks about V. So we use L to talk about V. So the language floats free from sets, right? It's part of our talk about sets and when I prove things about the language, I'm not really doing set theory. I'm just proving something about the syntax of the language. So the language kind of floats free from sets. So in a way, L floats free from sets. Wherever sets exist, the language exists somewhere else. Right? But now we want to express in set theory the fact that we can do model theory or chunks of mathematical logic, chunks of mathematics in set theory. So that means that we're going to want to have a way of talking about language in set theory. So we're going to see how to do model theory, right? Say a branch of mathematical logic. So it's a branch of mathematics. Within set theory. I mean, when we tried to do number theory in set theory, we had to take some sets as representatives of numbers. When we do number theory, so a branch of, again, a branch of mathematics, in set theory, what we did was we defined 0 to be, the empty set, and 1 to be set containing 0, right? 2 is the set containing 0 and containing 1, etc. All we were doing, we're not saying that the number 1 is this set, right? What we're doing is defining representative sets, which can serve as the numbers. So we choose representative sets to serve as numbers. We're not saying they are those numbers. Right? I mean, that's a different philosophical position. So we're not claiming that 1 is. We're just using this, as it were, as a code for 1. Code for, or representative for 1. Okay, that's for number theory. Well, we want to do some model theory of structures with languages. So what we're going to have to do is, again, choose representatives for, in particular, our objects of study, which will be formulae from the languages. So we shall need to choose representatives for the formulae in our language L here, just as we did numbers, representatives for numbers. So we can express facts in set theory about our formulae. Right, that's the overall framework. Right. Now, in principle, we can do this for any language. We could do this for the language appropriate for groups, or the language appropriate for fields, or language appropriate for databases. Anything that logicians call a first order language. Right? So in linguistics, people set up axiomatic systems to try and model linguistics, computer programming languages, right? All of these can be coded up in set theory in some way or other. Right? We're only interested in just our language, so we're going to restrict to just doing it for our language. But in principle, we could do this rather abstractly for any first order language. And in many textbooks, you'll see that done. But we'll save time. We're only interested in our language of set theory. Okay, I don't know if there are any queries. So Girdle first used this idea of coding up language. Right. Let's see if we can focus on that there. And so what we're going to do is kind of from outside, that's why we call it meta-theoretic recursion. On the structure of our formulae of our language, we're going to define for every formula phi its code set. And it's got little corners around it. You can see there, the phi has got, and these are sometimes called Girdle corners. Or so phi is the thing in our language that we've been talking about and writing down on paper. This is a set. So this set stands in the same relation to phi as the set with the empty set stands in the relation to 1. And our code sets will be members of the hereditary finite sets. Right? So a code set will be a finite set, all of whose members are finite, all of whose members are finite, and so on. And you can now see how the induction goes. We do this, we first define what the code sets for the atomics are. So actually for an equation, Vi equals Vj between variables, we'll use actually the number 2 to the I plus 1 times 3 to the I plus 1, 3 to the j plus 1. For an epsilon atomic formula, Vi's member of Vj, we'll code it using different numbers, 5 to the power I plus 1 times 7 to the power j plus 1. So if I've got a number of the right form, I can decode which type of formula atomic it's talking about, and whether it's saying Vi equals Vj or Vj equals Vi or whatever. So we define outright what the codes for the atomics are. And we, again, now we're going to choose a set to code a disjunction. And the code for the disjunction chi or psi, I'm going to assume I've already got, by recursion, a code for chi and a code for psi already defined. So a code for this disjunction is going to be this triplet here, this unordered triple. And it will consist of the code for chi, code for psi, and the singleton set which contains the code for chi. Of course, this is different from this. Right? And actually, the point of doing this is so that if somebody presents you with this set, you can look at it and then say, oh, this is a singleton of one of the others. So I know that's the first formula in the disjunction. If I just coded this by the unordered pair, I wouldn't know, given the set, whether chi was supposed to be first written down or psi. But by putting in this extra bit of information, I can twig or work out that chi is supposed to be the first formula in the disjunction. That's all. It's the only reason it's there. I will code not psi by the unordered pair set 0 together with the code for psi. And I'll code the existential formula, exists for the I psi, again as an unordered pair set. I assume I've already got a code for psi, and I'll throw into the set this prime, power of this prime, 11 to the I plus 1. So this way, we can code up formulae. So I can think of a formula as just sort of like a little tree with leaves on it. Right? So maybe if I've got some formula that's like this, there exists Vi such that Vi is a member of Vj, and it's not the case that there is a Vj such that Vj is a member of Vi. Something like this. So, and now you could just use that definition to recursively work out what the code of this formula would be. I mean, the code of Vi and Vj here, this atomic, is 2 to the I plus 1, 3 to the j plus 1 here. And then I'd look at the code for Vj and Vi here, and this will be the other way around. This would then be 2 to the j plus 1, 3 to the I plus 1. Here, this will be the code for Vj and Vi. And then you'd want to, you've got an existential quantifier in front of here. So then I put this, then inside 11 to the, well, j plus 1 here, and then this code for this Vj and Vi. So this set, this is this code right here. And this code then is this set. And you'll proceed down through here. Let's suppose this was a disjunction. And then you proceed down through here. So for the disjunction, you then put down in here a code for Vi and Vj. And then this code here, oh, I haven't done the negation. Negation then would have to have a 0 in front. So now I'd have to have 0 and then this whole set. Down here, and then disjunction would be putting these together here. Vi and Vj. And then I'd have this here. Well, that's the code for not exists Vj, Vj and Vi. And then according to my rule, I need a third thing, which tells me which formula comes first. Down here, this one. So I'd put this in here. So you get the idea. This is how we would code formulae up by these sets here. So I can tell a story about this. So this is called Girdle coding, and Girdle used prime numbers to do his coding when he was proving his incompleteness theorems. And this was natural because the theorems, after all, are about, his incompleteness theorems were, after all, about arithmetic and showing that you couldn't prove in arithmetic that arithmetic was consistent. Right? So he did this using this kind of prime powers that we saw for the atomic formulae here. But actually, how you do it isn't really important. Right? The coding that I just put on here was just something that I've wrote down for this course. Right? How you do the coding is not really an essential feature of it. So actually, I was on this radio program. It was about Girdle and Hilbert, and I forget. It's one of these Melvin Bragg radio programs on Radio 4. I can't remember. It was not Start the Week, and it was. Anyway, it was hosted by this Melvin Bragg, and there was this other mathematician, and there's also a cosmologist there on this, and so Marcus de Sautoy was who you may have seen. He's a talking head on BBC, often on kind of maths or science popular programs. So he was the mathematician, and so we all had to kind of sit around this tiny table and ad lib our remarks. And so when we were talking about Girdle and these incompleteness theorems and this coding, so Melvin Bragg turned to Marcus de Sautoy and said, "Ah, yes, this is where your prime numbers come in, Marcus." And so Marcus kind of shut his eyes and raised his hands to the heavens like this and said, "Ah, yes, the primes, yes." And then proceeded to talk about how important the primes were. But actually, it doesn't matter how you do the coding. You don't need to use, I mean, it's convenient in number theory to use the primes, but you don't have to do it at all. The actual means of coding, in some sense, like the least important part of it. So you shouldn't get too hung up on any particular system of coding here. And you don't have to memorize these clauses that are here. I'm not going to be asking you to actually do some coding or decoding. Right? A machine can do that. But we'll see how then we can use these code sets then to give a definition for a formula and give a definition then later for proofs. Okay, so that'll be in the recorded lecture for next time. Okay, fine. So bye for now. In our time. Yeah, that's what it's called. Thanks. I couldn't remember forever.